Welcome back, AP Stat, to Chapter 6, Scatterplots, Association, and Correlation. Let's look at scatterplots. The graph displaying the data of prediction error in nautical miles. By the way, those are different than land miles. Only the British could get away with this. Anyway, the graph here displaying the prediction error for the paths of hurricanes since 1970 is an example of a scatterplot. Since the x-axis is time, we can refer to this as a time plot. It's a scatterplot dealing with time. So we have our years on the x-axis, and we have our prediction error. This is, we make a prediction about where a hurricane is going to go, and how wrong we are is called the prediction error. Simply by observing a scatterplot, we can observe trends, and we're going to learn how to quantify those trends and determine whether or not perceived trends are noteworthy or if they're just kind of by chance. We'll be talking about some of that in this chapter, and much later in the year, we'll be talking about how to determine rigorously whether or not a trend is significant or if it's just incidental, if it just these points just so happen to form a linear pattern. And there's a great quote by Yogi Berra. Association, direction, and form. We have a positive direction for our association, which means that as x increases, y increases. Then we have a negative direction. As x increases, y decreases. These are both examples of a linear association, whether positive or negative. Though the points don't form a perfect line, of course, they do tend to move, as it were, in a linear direction, as opposed to these fellas over here, which are a bit grainy, my apologies, but they follow a nonlinear form. Here we have a curve, and here we have an even more interesting curve. There are scatterplots in theory and in practice that follow patterns like these. However, these are beyond the scope of the course. In fact, when we see a scatterplot that has a pattern like one of these, there are some tricks we can use to make it more like one of these without corrupting the data. More on that in Chapter 9. Now let's talk about the strength of association. If the points all seem to be gathered about a supposed line of best fit, we would say there's a strong association. If there's a clear linear pattern, but the points are a bit more chaotic in nature, we would say there's a weak association. And if you have trouble fitting a line through these data, whether you don't know whether to fit the line here, or whether to fit the line here on a diagonal, or, strange as it is, straight up and down, if you just don't know where to put that line, there's no association. Okay, if there's no pattern that you can clearly see, there's no association. It's just chaos. And that does happen sometimes. Now let's talk about outliers in scatterplots. When we see an outlier in a scatterplot, it deserves attention for one of two reasons. One, it could be a typo. Okay, someone could have put a wrong value in the data set. It could also be a really extraordinary instance. Hurricane Agnes was a hurricane in the 1970s that was horribly predicted, so horribly that the people of Harrisburg, Pennsylvania had no idea it was coming and had to do something they weren't used to doing, which is this kind of thing, ride around in boats rescuing people. Let's describe these scatterplots. We are going to describe the association in the scatterplots and mention the direction, form, and strength. And we're going to note any outliers And there is a possibility that there is no association at all, and we would just say something to that effect. Give each of these a go, talk about their direction, form, and strength, or say that there's no association. By direction, I mean positive or negative, form, linear or nonlinear, strength, strong or weak, or none at all. Okay, I assume we're ready to continue. The first one at the top left is a positive linear association that is rather weak in nature. There may be several outliers. The general trend is over here, so maybe some of these higher up fellas may be outliers. I don't know. Any way you slice it, it's a weak association. Let's look at the second one. That is a negative association. As x increases, y decreases. It is nonlinear. Good luck fitting a line to these data. It is going down, but it's not going down in a line. It's going down in a curved 1 over x kind of way. And it is a strong association. Whatever nonlinear pattern it follows, it's following it very closely. No outliers, at least none that I can see. Bottom left, we have a negative, linear, and weak association, and there may be several high outliers. All right, so the general trend is going down and to the right here, but these fellas seem to buck the trend, so maybe they're outliers, maybe they're not. And the last one has no association. You knew this was coming eventually. No association. And even so, this may be an outlier. With no association, it's especially tough to find outliers because everything's chaotic anyway. But that still may be an outlier, right? Now, there are more precise ways of finding outliers, as we've already discussed this year when talking about John Tukey and box plots. However, we're kind of just eyeballing it here right now. Hope that's okay. Let's talk about variables in the context of scatter plots. The variable of interest is called the response variable, sometimes called the dependent variable, but response variable is the term that shows up the most these days. This variable is mapped on the y-axis, or the vertical axis generically. The other variable, which is oftentimes, though it doesn't have to be, the example below is a case in point, is called the explanatory variable, which the old school term is independent variable, but explanatory variable I think is a better term, and that is the term you'll see more often, which is graphed on the x-axis. You might say that we're looking for whether or not a change in the explanatory variable explains a response that is modeled in the response variable. Okay? Is there a response worthy of explanation within our data? So we're going to identify the explanatory variable and response variable in the scatter plot to the right. And then we're going to describe the association between the variables, that is the direction, form, strength, and if there are any possible outliers. So the explanatory variable is our horizontal axis variable. So that's the weight of the car in pounds. Then we have our response variable, city miles per gallon, right? If you are a driver of a car, or even if you're not, you may be very well aware that driving through a city produces vastly different results than driving on the highway or through the countryside in terms of your gas mileage. All that stopping and starting really does reduce your gas mileage. So city versus highway, very different gas mileage numbers. Okay? So let's talk about the association. The direction is most certainly negative. The form, save for this chaos in the beginning, we'll talk about that in a moment, does seem to be rather linear. You could make a debate that it's curved, but we're going to go with linear unless we have strong evidence to the contrary. It's pretty strong for real world data. It's pretty strong. But possible outliers, the strength really wanes around the 2000 mark. My goodness, this is chaotic. You could make an argument that we have 3 outliers, at very least 2 outliers up here that are really messing with our data. So now we're going to create a scatter plot in the graphing calculator. We have the year versus a count of CO2. We're going to be making a scatter plot in the calculator so that you can create scatter plots of bivariate data like these. So here we are at the calculator, and I've already entered these data. What I'm now going to do is go into second, stat plot, and we're going to make sure the plot is on. Very good. And we set it to scatter plot. My X list, my explanatory variable, is list 1. That's the changing of the years. The Y list, that's going to be my CO2 count of something. In list 2, probably atmospheric in some location or worldwide. I'm not sure what the units are, but it's list 2, and it's the response variable. Okay, so, and the mark, you can choose whichever mark you like. I'm going to choose this little dot fella, and now I'm going to go to zoom, and if I hit zoom 9, you know what that is. It's zoom stat, and that is a linear progression if I ever saw one. Now we're going to talk about correlation, which is often confused with the term association, though there is a key difference. The measurement of the direction and strength of a linear association between variables is the correlation. So the relationship itself, as we have described it, is called an association between variables. But if we were to fit a number, a measurement, to the direction and strength of an association, that numerical measurement of an association is called the correlation. So an association is the actual thing. If we were to quantify the strength and direction of that thing, that's called the correlation. The variable for correlation for a sample is R. For a population, it's a Greek equivalent of R. It's called rho, as in row, row, row your boat. But you don't need to know that. You just need to know that R is the sample correlation. R is the slope of the line of best fit for the data points after they are standardized, okay? So the correlation is, if we were to talk about it mathematically, a slope. What kind of slope? It's a slope for the line of best fit for data points. How do we find a line of best fit? That's what Chapter 7 is about. More on that later. But R is the slope of the line of best fit for data points after they are standardized, okay? So before we standardize, that slope's going to be different than R for our line of best fit. But once we standardize those data, then we would have a slope, and that slope is R. Now, we talked about standardizing data values that are not bivariate. We talked about standardizing data values that were individual numbers, not coordinates. So how do you standardize a coordinate? Well, you ultimately don't need to know this for the course, but here is essentially how it works if you're curious. You take your scatter plot, and then you standardize for each point. Each point has an x and a y value. You take each x value, subtract the average x value, and divide by the standard deviation of the x values. This is the formula for standardization for one variable. Then we just do the same thing for the y values. If we standardize the x and y values of each point, we would get standardized points, hence the z's, z being a standard score. So after we do that with all the points, which I'm sure you can imagine is laborious unless you use a calculator or some fancy software, you would get a plot like this, okay? So in this scatter plot of z-scores, standardized x and y values, you have all these standardized data right here, and the slope of the line of best fit through these data is called the correlation. Here's how we would interpret correlation. This is extremely important. This is very important. Chaos, as you can imagine, has no correlation. You standardize chaotic points and you just get different chaotic points, okay? So no correlation. The slope of this set of chaotic points, if you were to fit a line of best fit through it, would just be a flat line, all right? Slope of 0. A low negative correlation would be, it's a bit chaotic, but there is a pattern that you can see, all right? This correlation would clock in at about negative 0.5. If we have a high negative correlation, a linear pattern is very visible, but it's not perfect. We would have a negative value that's close to -1. And in a perfect negative correlation, the ants are marching one by one. Hurrah, hurrah. Okay? On the other end of things, we could have a perfect positive correlation where the other ants are marching one by one, hurrahing as they go. If the ants are a little less disciplined in their ant ways, then we have a high positive correlation. Okay, so you can still fit a line through these data, and it has predictive power. More on that in Chapter 7. But the ants are not marching one by one. Okay, they're marching more like ants in the real world. Okay, so that would have a number close to 1. If the ants need to get sent back to ant boot camp because they lack discipline but still seem to be heading the right direction, you have a low positive correlation if the trend is up and to the right. There are some conditions we need to consider for the correlation, okay? The correlation is not meaningful unless the data meet 3 conditions. You can compute the correlation for any set of bivariate data, any set of data that is reasonable for a scatter plot. However, we want to make sure these 3 conditions apply before we actually try explaining things with the correlation. All variables are quantitative. That is, they are not categorical. Heaven forbid you try to fit a correlation to categorical data. I'll let you think about that for a moment. Oh man, that is not wise. You want to make sure your data are numerical in all respects. The data suggest a linear relationship. It does not have to be perfect. Remember, the ants do not need to be marching one by one or even close to one by one to say that there is a relationship. Okay? So, the data suggests some kind of linear relationship, even if it's a weak one. What that means, though, is that they cannot suggest a nonlinear relationship. If you have a curved relationship for your points, correlation's not going to help you. It's in the definition of correlation itself. It's a measurement for data proceeding in a linear manner. All right? We don't want to use correlation for nonlinear data. And there are no outliers, all right? Now, this is a tough one to follow sometimes. Sometimes we just straight up omit the outliers to find a regression line and just count those as weird cases. Sometimes it really messes up our data, and a regression line is going to be strongly influenced by those outliers. Again, more on that later in this unit, right? There are no outliers, since there can be no data points that could skew the otherwise strong correlation to look weak, or vice versa. All right, if you have outliers and the overall correlation is pretty strong, it could make the correlation appear all of a sudden weak, because correlation considers all standardized data points, not just the ones that we care about. There is also an instance, and I can show you this in class if you're curious, about how a weak correlation could be made out to be rather strong because of some outliers. Okay, that is possible, and I can show you that in class if you are interested.